Welcome everyone. My name is Asif Nawaz. In this video, I am going to discuss my master's thesis. It is titled Exploring New Frontiers in Imbalanced Learning, Data Complexity-Based Solutions. First, let's look at the contents. I am going to start with a brief overview on the imbalance classification problem. Then I will discuss the motivations and objectives of this research. I'll discuss my contributions. There are several contributions and several algorithms that I have proposed in this thesis. And then I'll conclude this presentation. Okay, so the imbalance classification problem. Now, class imbalance is actually a major problem in classification tasks. As you can see in the figure, when there is an imbalance in the data, unequal distribution of samples in different classes, where one class has too many samples compared to the other classes. So in such a scenario, the classification algorithms, especially the traditional classification algorithms, becomes biased towards the majority class. So the algorithm provides very high accuracy, but performance on the minority class becomes very poor. And especially in cases like, for instance, AI in healthcare, medical diagnosis, where we have very small number of minority class samples. So in those cases, diagnosing the positive cases is very important. And if the algorithm does not perform well in those cases, then our algorithm is not actually working basically. So that is one of the main reasons that we want to improve the performance on both the majority class as well as the minority class to have a much more reliable decision support framework. Now, learning from imbalanced data. So there are different algorithms that have been proposed to address this class imbalance issue, and they can be broadly classified into two categories. One is the data level approach, another one is the algorithmic level approach. Now, in the data level approach, we actually resample the original distribution in the data. Okay. So the purpose is to reduce the class imbalance as well as overlapping. And as for the algorithm level approach, we modify the cost function that we have inside the algorithm and apply higher classification cost, misclassification cost to the minority class instances. So if we look into these things, so the data level approach can be divided into 4 different categories. Oversampling is where we actually generate new instances from the minority class. So we have class imbalance like this. So we generate new instances so that the data becomes quite equal distribution is there. And in undersampling, we remove instances from the majority class to bring balance into the data set. That is the data level approach because we are modifying the data distribution. Now, a combination between undersampling and oversampling is called hybrid sampling. As for ensemble methods, all these oversampling techniques or undersampling techniques can be incorporated into the ensemble learning framework, such as the bagging framework or boosting framework. And that is the ensemble method for imbalance classification tasks. Now, in the algorithm level approach, in the default scenario, what we have is that we have a cost function where every misclassification is weighted 1. Both majority class, minority class, all are treated equally, and a loss value of 1 is assigned to them. But in algorithm level approach, we assign higher misclassification cost to minority class instances so that you can say the decision boundary actually changes because of that. And if we look at this figure, we can see when we increase the weight of some of the instances, how the decision boundary actually changes for the support information classifier. Moving on. Now, as for the algorithm, there are many different approaches are there, popular approaches for the oversampling. SMOT is the most popular technique used. Now, SMOT has lots of different variations. For instance, geometric SMOT, borderline SMOT, adaptive SMOT, and also there are for undersampling, we have random undersampling and inverse random undersampling, IST, that is instance hardness threshold. So different methods are there that have been very popular and widely used in the class imbalance classification tasks. For hybrid sampling, we have SMOT and ENN, where ENN is the undersampling technique and SMOT is the popular oversampling technique, and both of them just combined to produce this hybrid sampling approach. As for the ensemble approaches, we have BRF, balanced random forest, where random undersampling is incorporated into the bagging framework. For RAS boost, that same technique is incorporated with the AdaBoost framework. And this way it actually goes, SMOT bagging, SMOT boosting, things like that. Now, so what makes imbalance classification so difficult? So there are actually different data difficulty factors that actually increases the complexity of learning from imbalanced data. And this is actually a recent article published in 2021. Previously, more focus was put into the imbalance classification problem solely on the imbalance ratio. If the data is imbalanced, if we balance the data, performance will improve. But that is not the only reason. There are many other reasons behind that actually increases the complexity. And so those things are investigated in this article. And if we summarize, there are some of the main reasons. Number one, the rarity of the samples. Now, the more rare the minority class samples are, the more difficult it is for them to learn the pattern from those kind of data. And it is a very general statement. Imbalance ratio, naturally, when the data is skewed, the learning becomes complicated. But more importantly, there is another issue called class overlapping. So class overlapping makes it difficult for the classification algorithm to distinguish between the classes. And when the data is skewed, the presence of class overlapping actually further increases the complexity of learning those samples properly and identify the minority class instances. Also, noisy instances, there are always some noisy instances in the data. So in middle of a majority class, I have a minority class data sample. So these things also increases the complexity and increases overfitting. And a small disjunct is another issue. If we look at the figure, this is the class overlap issue. When you have samples in the minority class samples, the green ones, the circular ones. So when you have minority class samples in the region overlapping with the majority class samples, the triangular ones, that makes the classification more difficult. Samples that are further away are much more easier to classify. And as for a small disjunct, sometimes there are different minority class samples scattered around the data space, and that makes the learning more difficult compared to if they are actually located together. Now, the motivation and objective of this research is that there has been the development of a plethora of approaches for imbalance classification tasks, as we have seen before. And those approaches actually work well, but very few research has been conducted to analyze the efficacy of those techniques, how those techniques actually work in different scenarios. So we have found, for instance, some of the techniques work well in lower imbalance data, but they actually fail in high imbalances. So there is obviously some limitations of those approaches. So what are those limitations and how to actually overcome those limitations? So that is one of the main purpose of this research. And we want to use this understanding to guide the development of new and more robust approaches so that we can develop. Also, many of the techniques that have developed, they also have certain issue. They don't work well they work well in certain scenario, but they don't work well in other imbalance scenarios. So how to generalize well, how to generalize them well in many different data sets. Okay. So that is another goal. Now, most of the established approaches that we have, they don't take into account the data difficulty factors. Especially previous algorithm did not actually consider those data difficulty factors. But addressing those factors can improve the prediction performance, as we see in this thesis. Now, the contribution of this research, of this thesis that I have, I started out with a detailed experimental study on a wide range of datasets, around 100, 100 dataset, imbalanced datasets. And I tested most of the popular and state-of-the-art algorithms that is used in imbalance classification tasks. Okay, so that we can understand the limitations of those techniques and how they actually tackle the imbalance problem and how we can improve the performance from those approaches. Now, after that, I have developed a novel data resampling techniques. Okay, so that is aimed at minimizing the effect of those data difficulty factors that I previously mentioned, while also addressing the limitations of those approaches that I actually found. Now, then I proposed an ensemble approach that actually merged this data resampling technique into the ensemble framework to provide more generalized performance. Now, in terms of cost-sensitive learning, there are some limitations in the cost-sensitive approach, the standard cost-sensitive approach that is applied in the scikit-learn library or XGBoost library. And I proposed a novel approach that is instance complexity weighted classifier. So we'll discuss a little bit later. And for multi-class classification scenario, I proposed a novel data decomposition study, decomposition technique strategy for multi-class problem that is different than the popular OVO, that is one versus all or one versus one techniques, and aimed at improving the performance from those approaches. So let's start with this. So efficacy analysis of different techniques used in imbalance data. And for this research, an experimental study was conducted on 84 imbalance datasets, and 30 different techniques were used the state-of-the-art techniques that is used in imbalance learning. Now, the datasets are all public and they are available in UCI and GIL, and all of the datasets, the link to the dataset are provided in the GitHub folder. Now, we use two different classification algorithms for this research, SVM and random forest for this efficacy analysis. And a repeated five-fold stratified cross-validation was used so that we can get a more or less more generalized performance. And as for the performance measures, MCC score, ROCAOC score, and G-mean score was considered because these are gives more better results in imbalanced data. We cannot use accuracy or sensitivity for imbalanced data. We have to look into compound metrics like this way. So detailed discussion has been provided in the thesis book. I am not discussing those things in the presentation. And as for the imbalance ratio, the data sets can be divided into three imbalance groups: low imbalance, mid, and high. This is solely for easier of explanation. Awesome. Now, these are the data set that we have used. We can see from offer sampling, there are 12 offer sampling techniques, 7 under sampling techniques, 2 hybrid sampling techniques. So these are the techniques that have tested in this efficacy analysis, experimental analysis from all different categories. Now, as for the performance, if you look at the performance of the offer sampling algorithms, so as it happens when you test the performance, with the increase of the class imbalance ratio, the performance declines. If you look at here, the first one is the smaller imbalance, IR less than 10. The performance declines as IR increases from less than 10 to 10 within 30. And there is a major decline from higher imbalance scenario. But if you look at the overall scenario, the performance is more or less the same for all the offer sampling technique that we have used. All of them are more or less the variation of this mode algorithm. Actually, they are performed on average more or less the same. They don't actually provide significant improvement over the original SMOT algorithm. And as during the research, when we actually investigated these things, there are some other issues that we actually found. For instance, the reason that the performance actually drops in high imbalance is that in high imbalance scenario, we have to generate a substantial amount of new samples to balance the data set. And generating too many samples actually produce noisy samples and they actually cause overfitting of the data. That's why the performance drops significantly in higher imbalances. And the oversampling techniques that we use, they do not actually address this issue so far. The oversampling techniques that have been investigated, they do not address this issue. Now, undersampling techniques. As for the undersampling technique, there is a higher decline in performance compared to oversampling. If you look at here, for higher imbalances, the performance is lower than 40. That is the MCC score. Here, the performance was around 50 for high imbalances, but here it is lower than 40. So, undersampling techniques performs poorly compared to oversampling techniques. Okay. Now, that is because actually, when you have imbalance scenario, we are removing the data for undersampling techniques, and removing the samples actually cause loss of information. And so when we have loss of information, the classifier fails to do well, perform well in different scenarios. Also, another reason is when you are undersampling, they are not increasing the presence of minority class samples. Because if we have only 20 majority class, minority class sample positive cases, learning pattern from those only 20 samples is going to be difficult. And if you do not increase the presence of the minority class instance, that is going to cause performance drop and loss of generalization. Now, these undersampling techniques can be divided into two categories. One is the distribution-based approach, and another one is the overlapping-based approach. Now, distribution-based approach focus on balancing the data. So, as many samples to be removed, they actually remove so that the data is balanced. And as for the overlap-based techniques, they actually try to reduce the overlapping between the positive cases. So that way they can actually improve the performance, but both of them have serious limitations because they do not work well in high imbalances. Because if you look at overlapping-based approach, the number of samples that are removed by these techniques is very limited. So they actually fail to shift the bias that is caused by this imbalance problem. As for the distribution-based approach, removing so many samples causes information loss, and ultimately they are not performing well either. Now, as for the hybrid sampling techniques, the hybridization that have been developed so far, they do not actually provide much improvement of our response. They are particularly useful, highly impressed, but the algorithms are just mere combination of undersampling and oversampling. So they are not introducing anything new, just merely reducing, lessening the effect of of those problems that I have mentioned previously. But more research is needed so that actually this performance can be improved from these hybrid sampling techniques. As for the ensemble methods, actually the ensemble techniques, bagging or boosting, they do not solve the imbalance classification problem. So the performance do not actually much improve over oversampling or undersampling techniques. Actually, the performance actually drops, reduces when we apply ensemble methods because those methods in particular, they do not address the class imbalance issue. And when we perform bagging, the imbalance ratio actually increases. So the performance drops even more compared to the oversampling technique. So oversampling techniques actually works better. Now, as for the cost-sensitive technique, cost-sensitive approaches actually performs equally well with oversampling technique. They performs better than undersampling or ensemble, but they do not provide any significant boost over the oversampling techniques. They are more or less the same. This is the cost-sensitive approach. This is the highest performing oversampling technique, Lee. And we can see there is not much variation, more or less the same thing. Now, if we look at here, an example, if we look at here, so for instance, a data set has 10,000 samples and the imbalance ratio is 100. So 100 sample in the minority class and 9,900 samples in the majority class. So when you try to apply oversampling technique, the issue is that from that just 100 samples, we have to now generate 9,800 synthetic samples. Now generating so many samples from just only 100 samples, that causes some issue. Issue is like they do not always match the characteristics of the original minority class. So this actually causes loss of generalization. So this kind of excessive oversampling leads to overfitting. Also, when you're generating so many samples, there is going to be some noisy samples generated. Also, generating samples actually causes more overlapping. And the dataset size, so since we have already generated 9,000 samples, so the dataset size is now from 10,000, after oversampling, the dataset size becomes 20,000. So if we have 1 million sample, dataset size is going to become 2 million in this scenario. So the dataset size increased. So the training time will actually increase almost double. So these are some of the major issues with the oversampling techniques that we have seen so far. Now, as for the undersampling technique, again, to balance this data set, we have to remove 9,800 samples from the data. That is a extreme amount of information loss. So the performance actually proves significantly. That's why we have seen that undersampling techniques performance the poorest. Now, as for the overlap-based approach, overlap-based approach do not remove mass samples. So they may remove 800 or 1,000 samples. So still, then the imbalance ratio will still be 90. So that they do not actually solve this imbalance classification problem altogether. So their performance is also poorer compared to other techniques. Now, as for hybridization, they actually don't solve the problem, but they just palliate the situation. And as for the ensemble, okay, they actually rely on the oversampling and undersampling. So they do not solve this problem either. And it's just the underlying oversampling technique, undersampling technique that is actually trying to give better performance. And that's just what they are doing. Now, moving on. As for the cost-sensitive learning, so in cost-sensitive learning, all the minority class instances are penalized. Penalized like the default value is imbalance ratio, so 100. So the weight of the minority class samples become 100 for all the minority class samples. And this is the issue because when you actually penalize so many samples with 100 times larger than other samples, this is going to cause some distortion in the decision boundary. And so if we actually penalize some samples that do not need that kind of penalization, so this kind of unnecessary high penalties actually biases the prediction towards the minority class. So there are more misclassification of the majority class instances. So overall, when you test the algorithm, the performance actually drops significantly due to loss of generalization and overfitting. So the solution that we actually provide from this research, at first, for the cost-sensitive learning, ICOST, an instance complexity-based cost-sensitive learning framework is produced. Unison that actually tries to jointly address class imbalance overlapping, that is a sampling technique. IBRF, that is a improved version of the balanced random forest classifier and ensemble method, and another strategy for multi-class classification. Now, I'm going to discuss these things one by one. So I first. Now, in the traditional classification algorithms, all the misclassifications are treated equal. Penalty is one. Now, as for the traditional cost-sensitive algorithms, the multi-class instances are penalized heavily and according to the imbalance ratio. So if the imbalance ratio is 100, all the multi-class samples are penalized 100. So that is like 100 times more weight than any majority class instance, so that the performance on the multi class improves. But assigning higher penalty for misclassification, this actually deforms the decision boundary, and the bias now shifts towards the minority class in turn from the majority class. So the performance of the majority class actually drops significantly. So overall, the decision system, the support decision framework, they actually work well in the minority class, but they work poorly, just work poorly on the majority class. So overall, the prediction framework is less reliable. So we want to improve the performance, and the way we actually propose is that the main issue is all the multi-class samples are treated equally. Now, if we look at this scenario, some of the samples are located in the overlapping region, the circular ones, multi-class samples, but some are located far from the decision boundary. For instance, this green one. So this green one does not need to be penalized 100 times higher. Also, the red sample here in the middle of this multi-class instance should not be penalized, and the yellow sample here, both should not be penalized equally. The instances that are closer to the decision boundary needs higher penalization. Instances that are far from the decision boundary needs a smaller penalization is okay for them. Now, if we actually penalize like this way based on their complexity level, it will actually reduce the bias that actually generated, and the number of misclassifications, it will be able to generalize well when we are testing the data. So overall, the performance should improve this kind of application. And this is actually the proposal from this algorithm. Now, the solution is that we categorize the multi-class instances based on their difficulty levels, and we use the neighborhood search algorithm. So high misclassification costs are assigned to those samples that are hard to learn in the overlapping regions, and samples that are in the safe zone, they are actually penalized by marginal ways, not much higher compared to one. So this actually provides some more plausible weighting mechanism. So this is the algorithm that we have seen that we are actually discussing. So we divide we categorize the multi-class samples into three categories. Pure samples, the green ones, they are actually located far from the decision boundary. They do not have any surrounding majority class samples. So if we apply KNN, there is no chance that they are going to be misclassified. So these samples are not penalized significantly. Now, safe samples, the second one, are the yellow ones. They have one or two majority class samples in the neighborhood. So we need to penalize them a little bit higher to get them correct. And as for border samples, they are actually surrounded by 3 or 4 or 5 majority class instances. So we need to penalize them higher so that actually the model can actually perform well and correctly actually classify them. Now, in the algorithm, inside the algorithm, there are different approaches that we have actually used. One of them is the generalization that based on the number of surroundings majority class instance, we have created them from G0 to G5. So G0 means no surrounding opposite class instance. G1 means there is only one opposite class instance out of 5. So K value of 5 was utilized. So this is the ICOS framework. We have applied those algorithm by inheriting from the scikit-learn library classifier. So we can apply support vector machine, decision tree, logistic regression, as well as random forest classifier. Now, there are 4 different types I have tested. So original means the original implementation of the cost sensitive. INS, that is the instance complexity-based classifier that we are proposing in this algorithm. But for the benefit of the user, for flexibility, there are other weighting mechanisms that can be utilized. One is generalization. So the user can actually choose what weight they want to produce to G0, G1, G2 separately. If they want to do it, they can actually provide it. That is for actually for providing much more flexibility in applying this algorithm. And NAP is for Napier-Rela. There is another paper from Napier-Rela where he actually proposed to classify the instances, multi-class instances, into 4 categories. So that is only suggesting from that one. So we also keep that one in our algorithm framework. Now, cost factor is another parameter where we actually define the cost. We can define it as a list or a dictionary or integer, and some default values are chosen. based on our analysis, we have fixed some default values. Now, but to get the proper cost factors, there should be some searching algorithm will provide the best cost factor that actually optimizes the prediction performance. So we can use grid search or randomized search. Evaluation algorithms can also be used. That is going to be that is likely to be get the best results. Now, for instance, if we call this algorithm like this way, I cost on the data, we have the classifier SVM and cost factor 2010-3. So a cost factor, that is the misclassification cost of 20 will be assigned to the border samples, 10 will be assigned to the pure samples, and 3 for the safe samples. So this is the way we can actually, this algorithm actually works. Very simple and straightforward. The code is already provided in the GitHub repository. Now, as for the experimental setup, we tested with 3 and 4 classifier. Later, I add another classifier, random forest. And the performance was tested on 66 imbalance classification, and repeated stratified cross validation was used. And grid search technique was used to find the optimal scenario, so optimal optimal cost setting, both for Dodge and in instance. So this is the performance that we have achieved. This is the performance from Dodge regression classifier. We compared the algorithm with the traditional cost-sensitive approach that is actually available in the scikit-learn library. Scikit-learn has the weighted classifier mechanism. So if we look at here, so on the 66 data sets that we have tested from 0 to 66, x-axis we have those data sets. And this is the changes in the MCC score, how much change was there. So as you can see on the first data set, the MCC score improved by 1%. On the second data set, there was no change, and so on and so on. So some of the data sets, there are very high change, 6%, 7%. One data set, there is 12%. And there is one data set that is probably around 56 or 57 data set where is a small drop in performance. So overall, we can see for the loss regression classifier, the performance improved in terms of the MCC score. And this is for the SVM classifier, we can see. Similarly, we have for most of the cases, there is a change in performance, there is an improvement in MCC score that we have achieved. Some of the data set, there was no change. So actually, the traditional cost-sensitive approach and our proposed algorithm both are actually working the same. And one particular data set, there is a huge gain in performance. Now, this is for the DT classifier, decision tree classifier. For some of the cases, the performance actually reduced by a small amount. There is around 5 datasets where the performance dropped by -1 or -2 maximum. But for other cases, there is an improvement in performance. So we can see overall, the ICOST algorithm that we are proposing actually improving the performance of the traditional classifier. The performance vary from 1 to 3%, but there is always some improvement. Most of the time, there is some improvement from the algorithm. And we also compared the algorithm with some of the popular approach, the sampling techniques, although that is not the purpose of this algorithm. We want to focus on the high cost with the traditional cost-sensitive approach compared. So these are the algorithms we have also tested, and overall compared to these traditional approaches, the ICOST framework actually performs well. It produces the better MCC score, better GB, and this is the average score on the 66 datasets, and provides better score on top of all of those things. Now, this is the second algorithm that I'm proposing, that is UniSym, a unified sampling framework to jointly address class imbalance and overlapping. So as for this algorithm, this is actually more highly engineered algorithm because there are many sampling techniques that have been developed, and during the efficacy analysis that we have performed, we have analyzed those algorithms and try to find what are the limitations of those techniques. So this algorithm is particularly focused on trying to improve on those, improve over those techniques. So the data difficulty factors that we have already discussed previously that actually complex the learning task. We can see there are 4 of them are major: imbalance ratio, the overlap between the samples, the rare samples, and the noisy samples. See, but they are actually much more related. Related how? Imbalance ratio is not the only thing that actually harms the prediction performance. A data can be imbalanced, but if there is no overlapping between the classes, the classifier can still perform very well. Okay, it can provide very high accuracy if there is no overlapping. A support vector machine classifier can easily draw a decision boundary, but that does not really happen in real world scenario. In real world dataset, there is always some overlapping between the classes. So overlapping is more related to the imbalance ratio scenario. But the algorithms that have been developed so far, they do not actually focus on both of them together simultaneously. Rather, they focus on either on the imbalance ratio or on the overlapping scenario. What we try to do, we try to provide a unified approach that can address both the imbalance ratio as well as the class overlapping together so that we can get better performance. And that is the main idea of this algorithm that we are proposing. Also, we are trying to improve the presence of the rare samples and reduce the noisy samples in the process as well. So if we look at the algorithm, so these factors are connected. That's what we just discussed. Now, the algorithm can be divided into three stages. So as you can see, first part is the oversampling. This is a hybrid approach. It actually takes into consideration takes into three different algorithms to actually produce the ultimate algorithm. So the first part is oversampling. Now, a modified version of the SPON algorithm is utilized to increase the presence of the microclass samples for data cleaning. And data cleaning is to reduce the overlapping as well as to remove the noisy instances. We use the neighborhood cleaning rule algorithm. And we also use random undersampling to reduce the class imbalance. So all these things together actually produce out the algorithm, the framework that we're actually proposing. So let's see how it actually works. Now, the original SMOT algorithm or the variation, the problem is that they do not use any specific selection criteria for interpolation. For instance, if we look at here, within these two samples, the black 2 R1, this sample is generated. But this samples is actually false between two majority class samples. So that is likely to be a noisy sample. Okay. And this is also increasing the overlapping. But this kind of selection criteria is not considered when applying the SMOT algorithm. So the general application actually causes this kind of overfitting scenario. Some instances are created in the among the major class instances that actually increases overlapping, but they do not actually generalize well when you are testing the data. That's why the performance actually drops. And we want to improve on that one. That's why we have developed a modified version. So the solution that we actually propose, that is limit the number. So one other thing that was issued that how many samples are generated from the SMOT algorithm if we want to balance the data set. But in our proposed algorithm, we don't want to balance the data set, but we want to increase the number of instances, but limit it by a hyperparameter alpha. So this is actually for by default value is kept at 0.5, so 50% increased. So not entirely, so that we can actually reduce the effect of too many sample generation. As for the customer's version, similarly, here the microclass instances are categorized based on their complexity level. Okay, and based on that, we generate the instances. Okay. As for the noisy samples, they are always generated by the application of the SMOT algorithm. And in the subsequent stage, we add a noise removal technique, that is an undersampling technique, to get rid of those noisy and overlapping instances so that we can get better performance. So it works unison with other algorithms, not a standalone. So the modified SMOT algorithm, same way, we have divided the dataset into three categories. For this one, we used outlier, safe, and border, and different names, and different selection criteria as well. So as for this one, you see the outliers that are actually completely surrounded by instances from the opposite class. Now that instance should not be selected to generate new instance, because that is going to generate more noisy instance and overlapping regions. So we want to avoid that completely. That's why the outlier instances are left out, and only samples are generated in the safe and border samples around those samples. That way, we can get a more reasonable generation of multi-class instances. So after that one, so we can see this data cleaning approach, neighborhood cleaning rule. This was actually proposed previously in another We are just using this algorithm. This actually provides a cleaning, but we are using this not standalone, but after applying this SMOT algorithm when we have generated new samples. So if there are some overlapping samples generated, then those samples will be removed, and it will clean the decision boundary of those samples. So this way, some of the noisy samples will be removed, the overlapping samples will be removed, and we'll get a much more organized data sets. And we can see the sample removal process from LCL here. Now, this stage actually accomplishes three goals. It clears the decision boundary, it reduces overlapping, also it actually reduces the imbalance ratio as well. Previously, I said we do not completely balance the data set from this one. We balance it up to 50%. So this approach actually reduces like undersampling. So 20% samples are taken. So the imbalance ratio becomes lower and lower gradually. And in the subsequent step, we use a random undersampling approach. We can use another undersampling, but I have used random undersampling because it is very fast and we can apply it without increasing the time complexity. So this one actually removes only 20%, not much. In the general algorithm, too many samples are removed. So we have limit that one, constraint that one by only 20%, controlled by parameter beta. We can tune that parameter as well. So only a selected few number of samples are removed so that we can actually reduce the imbalance ratio while improving the, while addressing the class overlapping scenario as well. So all these three stages collectively actually provide our unison algorithm that collectively performs well in terms of imbalance data. So we have tested this one for SVM classifier, as you can see. We have compared with many other algorithms, some of the most recent and state-of-the-art sampling techniques. And this kind of hybridization actually provides a very good improvement. We can see, for instance, this one, the proposed algorithm for the SVM classifier, we have 79.5, that is a G-mean score, where for the LVQ score, we have 73. There is like a 6% improvement in the G-mean score. That is significantly high. Also, if we look at the MCC score, that is for the polynomial field score, that is 47, and and we are getting 49.7, so that is like a 2.5% improvement over that algorithm. So the proposed algorithm actually performs significantly well. It also produces the highest sensitivity. So overall, this kind of modification actually improves the prediction performance. So the results are all provided in the GitHub folder, GitHub repository. And this is same for random forest as well. For the random forest, also the performance is very improving very significantly. So if we look at the random balance, that is the hybrid sampling approach, that is 62.9. And compared to that, the proposed algorithm is producing a G-mean score is 80%. So it is providing much more balanced prediction performance. The problem with the previous approach is that they provide good sensitivity, but poorer specificity, or the other way. But this proposed algorithm actually provides a good sensitivity, provides a good specificity, so that we can get a much more reliable prediction framework. Okay, that is one of the goal, and that is actually has been achieved in this. Now, the third one, that is IBRF, so improved balanced random forest classifier. Now, random forest classifier uses bagging approach. Okay, and bagging approach actually uses bootstrap aggregating. Now, the balanced random forest classifier that was actually proposed previously, they actually balance the data set of all these bootstrap samples using random undersampling. But we have seen previously that random undersampling algorithm, the issue with this one is that too many samples are removed, and that actually causes a major loss of information. So that does not work well. So BRF classifier, balanced random classifier, does not work well in imbalanced data. So we want to improve of that one. And to do that, we actually produce a modified framework. So when the data is actually, the issues with the original algorithm is that when the data is skewed, bootstrap subset, they become even more skewed. That is the bootstrapping process. It randomly takes data from the original data and put it there. So some of the data sets, there are much more imbalanced than the original algorithm. And so some of the subsets can actually lack mitotic samples entirely. So there cannot be no mitotic samples in any of the subsets. That can also happen. So the solution that we actually propose, that we propose a modification in the bagging framework. We include all the mitotic samples because they are limited in each of the bootstrap sample. So we first fill up those bootstrap subsets with mitotic samples. Then we add majority class samples randomly. Okay, that's how we can actually tackle this problem of imbalanced scenario. That is the first chance. And the second chance is, even after that, there can be some imbalance in the data. And to get through that, we actually use the proposed algorithm that we have earlier used, Unison. So we use that one for actually sampling algorithm. So each of the bootstrap subset are now resampled using the proposed Unison algorithm. That's how it actually works in combination. Okay, so if we look at here, so this is the proposed hybrid sampling approach that is now applied in the modified bagging framework, and that's how this is actually integrated. So as a result, we can get reduced information loss because we do not have that level of imbalance in the original data, and we also get better generalization compared to the original algorithm that we proposed. Better generalization comes from the bagging approach that we're using. So if we look at the comparison, and this is the IBRF that we have proposed, and we can see it is producing highest MCC score. It is also producing higher MCC score compared to other ensemble algorithms as well. This is smart bagging, offer bagging. These are the other ensemble algorithms, and it is actually producing like 5% improvement over those algorithms. So the performance improvement is significantly higher compared in this approaches. So this is the score that we have. And actually check this one. We are getting highest MCC, G-mean, as well as the RSS score. Achha. Now, this algorithm, this is the last one that for multi-class classification. This is a work ongoing. I'm currently working on this one. So, in the multi-class classification scenario are much more complicated. These algorithms, the previous three algorithms that we have proposed, they are equally applicable for multi-class scenarios. But there are some issues in the multi-class scenario that when you have multiple classes, we have to divide the algorithm. So the most popular approach is the decomposition-based approach, where we use either one versus one approach or one versus all approach. But both of them has some limitations. For instance, if we look at here, when you use one versus all, the data becomes significant. Yeah, the class imbalance becomes higher because now all of them back together and one of them separately. So class imbalance actually increases this kind of one versus race approach. So we have to address this issue. So for this one, we actually proposing a decomposition study. So try to address this issue by gradually solving the problem based on class imbalance as well as the overlapping issue. So this algorithm is currently under development, so I'm not discussing it here. I will add it in a different lecture. So there are some limitations of the algorithm. For instance, instance complexity, we are actually using the nearest neighbor approach. So there are other data complexity methods that we can actually use for that algorithm, and we plan to incorporate that in future. Also, same for unison algorithms. So the machine learning algorithms are rely heavily on data. So when you have highly imbalanced data, the algorithms cannot actually go over a particular range. There is a limitation. So since because of this highly dependent nature of the machine learning algorithms, this is the representational bottleneck. So we can actually try to improve the performance, but there is always has some limitations that our algorithm can actually go. So the conclusion is that you see in this thesis we have explored some of the new values that was not explored before. We are working with focusing on the data complexity issues like the ICOST algorithm entirely on the data complexity that was not applied in the scikit-learn library, and that we are actually proposing to incorporate that one in the scikit-learn library. Same goes for unison algorithm. The sampling techniques so far actually focus on either focusing on the overlapping instance or reducing overlapping or reducing imbalance ratio, but they don't try to go into the actual problem origination of the problem. So that is something that we're actually trying to address those things. So these are the approaches that we're proposing, and we believe that this research will provide a new direction in the imbalance scoping. Okay, so thank you. So we have, as for the publications, there are two papers I have already published, and two other papers is currently under review, and hopefully we are waiting for the review. Thank you very much for this.